Properties of solutions, a review. Reminding ourselves what a solution is, right? It's a homogeneous mixture. So the two substances retain their properties. They're just in the same proximity as each other, and it's an even distribution throughout the mixture. So there's the solute, the thing in the smaller amount, the solvent, the thing in the greater amount. The solvent surrounds the solute. So in a solution, a solute is dispersed uniformly throughout the solvent, right? That's important to understand, right? So the concentration on one side of a sodium chloride solution is the same as the concentration on another side of a sodium chloride solution. And right, we see a very nice picture here of the solvent water surrounding the different cations and anions, right? The positive side of water surrounding the green balls, which are the anions, and the negative side of water surrounding the purple balls, which are the cations. All right, solubility. How much solute can dissolve in a given amount of solution, right? Until we get what's called a saturated solution. So saturated solution, we haven't gone over what this is yet. I'm going to talk about it in this topic. So how much solute can I get to go into a solution? That's what saturation is. We've talked about electrolytes and non-electrolytes, right? Electrolytes are substances that when they dissolve in the water, they dissociate in such a way that they form ions, whereas non-electrolytes can dissolve in the water but may not form ions, right? If there's no ions, it doesn't light the light bulb. So current's allowed to run through the water as long as there's ions in the water, an electrolyte. So non-electrolytes, no ionization in the water. Weak electrolytes, incomplete ionization and ionization. So weak acids, weak bases, and strong electrolytes, complete ionization. Soluble ionic compounds and strong acids. Hydration is just solvation with water, right? So again, the negative side of water is attracted to the cation. The positive side of water is attracted to the negative anion. So it's the polarity of water that makes it the solvent that it is. All right, so polar things will be able to be dissolved in water. And we'll talk about why in a minute. All right, types of solutions. All right, so this is new. We subcategorize solutions as either being saturated, meaning that I've given the maximum amount of solute that can dissolve in that particular solvent at a temperature. Unsaturated, meaning I could dissolve more of the solute into the solution until I hit the saturation point. And then supersaturated is an odd thing where what you've done is kind of tricked the solution. You've gotten more solute dissolved at a particular temperature than there should have been. And you get what's called a supersaturated solution. And then we get a very dramatic effect when it drops out all at once. So saturated this is something I was always, well, going back to the definitions, this is something I was always I always misunderstood. I always thought saturated was like the equilibrium point where you hadn't quite put enough of the solid in there to go supersaturated. Well, that's not the case. Saturation is when you've put enough of the solute in there that it's dropping out. It's a solid on the bottom. So when you add enough salt or sugar or whatever to the water so that it's piling up at the bottom as a solid, that's a saturated solution. You've put as much solute into the solvent as possible. You've reached the saturation point. As opposed to unsaturated, where you could put more of the solute into the water and have it still not drop out, right? As soon as solid starts forming on the bottom, then you've hit the saturation point. Supersaturated, like I said, a weird situation. You've tricked the solution in a very dramatic fashion. What you can do is add a seed kernel, all right? It's a crystal. And then all of a sudden, all the solid will start forming a crystal off of that, and it'll all drop out at once. So again, it's almost like you tricked the solution into holding more solute than you should have by increasing the temperature and then decreasing it kind of rapidly. All right, a molecular view of the process. So what goes into Energetically, what goes into forming a solution? Simply put, three processes affect the energetics of the solution. So the solvent has attractions between each other. Right? If we're talking about water, it's hydrogen bonding. If we're talking about the solute and the solute sodium chloride, there's an attraction between the sodium ions and the cations, right? That's Coulombic attraction, electrostatic attraction. So it would take energy to separate those sodium ions from those chloride ions, right? That's an endothermic process. So you'd have to put energy in to what we call expanding the solute. And you'd have to make room for that solute to fit into the solvent, so that you'd have to expand the solvent. So endothermic, expand the solute. Endothermic, expand the solvent. Now there's going to be attraction between the solute and the solvent. So when you mix them together, that exothermic part is the surrounding of the solute with the solvent. So as long as the solute-solvent interaction collectively is greater than the expanding the solute of the solvent, you'll have an exothermic heat of solution. If it isn't, you'd have to put in more energy to expand the solute of the solvent in order to make the solution. Well, first of all, it might be a reason why these two things are insoluble in each other. It might just be too much energy to expand the solute of the solvent. So this is why they don't mix. It's why oil and water don't mix. Too much energy to put in to expand the water versus the energy release you get when the oil surrounds the water. So maybe they won't dissolve in each other. This is energetically the reason why. So expanding the solute and the solvent costs energy. You get a release of energy when the solute surrounds the solvent. So delta H1, delta H2, plus delta H3 should give me a delta H of solution. How much heat is required or released in the solution process? So an endothermic heat of solution, you're putting in more energy to expand the solute and the solvent than you're getting out when the solute expands surrounds the solvent. So it's Hess's law. Right? You can go in steps. Exothermic heat of solution, you're getting more heat released when the solute surrounds the solvent than you have to put in to expand the solute and the solvent. So you get a heat release when the solute surrounds the solvent. So add delta H1 to delta H2 to delta H3, you would get the overall heat change in the solution process. So solid sodium hydroxide turning into aqueous, solid potassium hydroxide turning into aqueous potassium hydroxide. We could look up the heat of formation for the solid. We could look up the heat of formation for the cation and the anion, and we could plug it into Hess's law, right? Prox minus reactants, and get the heat change. So it's the other way of doing it, right? We could look up the delta H's of formation of the reactants and the products and get what the heat change would be for the solution process. So solid ammonium nitrate, heat of formation of negative 366 kilojoules per mole. Aqueous ammonium nitrate, heat of formation of negative 340 kilojoules per mole. When I subtract prox minus reactants, I end up with an endothermic heat of solution. Well, if we remember our solubility rules, anything with ammonium ion is soluble. Anything with nitrate ion is soluble. So why the endothermic heat of solution, right? I'd have to put energy in to make this happen. It kind of implies that ammonium nitrate would be insoluble. So there must be something else besides heat driving whether something dissolves in something or not. Why does it dissolve at all? The answer is entropy, and we'll get into entropy more in depth later on in the course, but entropy is a measure of disorder of a system. And we have a third law of thermodynamics that says that I forget it's the second or the third, a law of thermodynamics that says the entropy of the universe, or the entropy of the universe is always increasing. So we live in a disordered universe. That's the more natural outcome of things, the more probable outcome. So anytime you have a system that's becoming more disordered, that's a more likely system. So if you have a positive sign on disorder, this implies that you're going towards a more natural state. A more natural state is a more disordered state. Whereas a negative sign on disorder means you're becoming more ordered. And that means you got to put energy in some fashion in order to order something. So a less natural state. So an entropy increase of the system tends to lower the energy of the system. All right, so we'll talk about the relationship between entropy and energy later on. But for right now, you can have an endothermic heat of solution and still have a solution process happen or something be soluble in something because you're becoming more disordered. So again, it's going to be a question of energy input versus how disordered you're becoming. So a spontaneous process, something that's going to happen, tends to happen when you lower the potential energy, right, an exothermic process, release heat energy, and you become more disordered. So a positive sign on delta S and a negative sign on delta H. So it's the two things, heat change, entropy change, that go into whether something happens or not. Axiom is like a saying, like dissolves like. So if you have a polar solvent, it'll more than likely dissolve polar solutes. If you have a nonpolar solvent, it'll be able to dissolve nonpolar solutes in it. So hydrophobic means water loving. So if you have a hydrophobic solute, it'll dissolve in water. If you have a hydrophilic water loving, right? So means it'll be soluble in water. Hydrophobic means water hating. So fat soluble. I mean, it'll dissolve in nonpolar solvents like oil. So oil is hydrophobic. It won't dissolve in water. So it's all about the solvent, right? A polar solute takes energy to expand the solvent. So as long as we're getting a strong attraction between the polar solute and the polar solvent, then it'll be sufficient to overcome expanding the solvent, right? The fact that we have strong attractions between the solvent particles. If I have a nonpolar solvent, well, then the interaction between the nonpolar solvent and the polar solute will be insufficient to overcome solute-solute attractive forces. I don't know, this should have been an easier way of writing this. The bottom line is do you get a strong enough attraction between the solute and the solvent to overcome expanding the solute or the solvent? So with a nonpolar solute and a nonpolar solvent, yeah, it's not a lot of energy to expand either one, and you don't get a strong attraction between them, so it's the entropy turn that's dominating, right? You're increasing disorder when you put gasoline into water, right? You want to get gasoline off your hand, or you want to get oil off your hands, use something that's nonpolar like gasoline, and you're increasing the disorder, and one will be soluble in the other.